Okay. So abundance estimation with capture, recapture data. We've talked about methods for estimating abundance so far. We're in this this chapter on estimating abundance and the different methods we can use to estimate abundance. We've talked about complete census, which we can rarely do in wildlife populations. Plot sampling is a method we can use when our detection probability equals 1. We never fail to see any animals within our transects. And then distance sampling is a way to address false negative observations or a failure to detect an individual when it's really there if the probability of detection decreases the further away we get from the center of a transect. And in addition to distance sampling, we're going to talk about mark recapture methods. So mark recapture methods are really popular methods for estimating abundance. And the basic mark recapture model is the Lincoln-Peterson method. And it's a very simple application. It has some fairly strong assumptions, but if you can meet that assumption, this is a nice method for estimating abundance. Because of its simplicity, its relatively ease of data collection, and well-developed estimates of uncertainty. Okay, so like I said, Lincoln-Peterson method is the simplest mark recapture model for estimating abundance. There are 2 trapping occasions. You trap some animals, you mark them, you let them go, and you trap some more animals, and you see how many of the second batch of trapped animals have been marked. So these methods and concepts have been around for a long time. Like many of the methods in statistics, Laplace developed methods related to Lincoln-Peterson estimators in 1786, and he used these methods for human populations. So here's an example, and this is an example that's posted on the web, kind of a popular example in demonstrating how we use mark recapture to estimate abundance. So we have a population of snails, garden snails, in a relatively small garden. We want to know how many there are. They're sometimes hard to find, but so we can't count them all. We can't do things like distance sampling, but we wanted to get some idea, and we're going to use mark recapture methods. Here are the snails. The idea is we're going to capture some snails, put little marks on them, and then release them. So in our first go, we capture, what is that, 9, 10, 11, 12, 13 snails. We put marks on them. We can put individual marks on them so we know which individual there are, or we can put just general marks on so that we know that they've been captured, but we don't necessarily know which one has been captured. When we give them individual markers, that allows us to relate individual traits to abundance estimates, and that becomes important when we start looking at survival methods, mark recapture methods for estimating survival. All right, so in our first count, we have 13 snails. That's how many we captured. This is going to be Y, our data YT. Now we release these individuals back into the population. We let them redistribute, give them time to rearrange themselves, and then we recapture a segment of the population. Suppose we recaptured this segment of the population. Some of the snails had been previously captured, and some have never been captured. Then we count how many new animals there are that include the captured ones, how many have that were already captured, and we can estimate 2 quantities, the abundance and the detection probability. And it follows methods similar to what we have already used. So we can set up this general model that we've talked about before, this binomial regression model, where we have Y of t comes from a binomial distribution with our abundance N of t and our detection probability P of t. So we've talked about this already in our Bernoulli regression models, our binomial regression models. We have a lot of 0, 1 data, And we have a lot of cases where we have counts that are only a proportion of the total number. And in those cases, we can use binomial regression models. So let's talk about each one of these components of this model. Y of t are the number of animals captured at time t. So y1 would be how many animals you originally captured. And y2 is how many you captured in your second event total. N of t is an unknown population size, and this is the parameter that we're trying to estimate. So this is an unknown value that we want to estimate, and we want to put uncertainty around. P of t is also a unknown detection probability at time t. So P of t now is another parameter that we're estimating, and that represents how many we capture, the probability of successfully capturing a snail given the total number of snails that are out there. M of t is going to help us estimate our detection probability P of t, and this is the number of captured animals with a mark at time t. Now we don't see this in here right now, but we're going to come up to it in the next slide. It shows us how it helps us estimate P of t. All right. So a question then, we have two samples of snails. The first one's just a count of how many snails we captured. The second one includes a total count, but it also includes this M of t, which is the number that were marked from the previous one. And we're going to use this information to estimate our detection probability P of t. All right, 13 snails were marked and released. In our second population, we captured 3 of those ones. How do we estimate P of t? Well, P of t is the number captured that were marked divided by the total number of captured. Makes sense, right? You put out 13 snails that were marked, and the number that you recapture in your second sample divided by the total number gives you your detection probability, your estimate of detection probability. So it's like you're treating these marked individuals as a little mini population within the entire population. And then the ones you recapture, M of t, divided by the total number marked, Y of t, tells you the proportion that you recapture the second time. Now you just have to generalize this little mini population to the overall population, make that assumption that this little mini population also represents the entire population, and we can use that to estimate our detection probability. Okay, so now that's P of t. The next question is, we know Y of t, we know M of t, and we have an estimate of P of t. How do we use these information to go back to N of t, what we're really interested in, and that is the population size? Okay, so we have N of t equals Y of t, the number we captured in our second sample, divided by P of t. So the number we captured divided by the detection probability gives us our estimate of the total number of snails in our population. You can also write this as Y of t, the number captured in the second occasion, times the number captured in the first occasion, divided by M of t, which is the number of marked individuals. And what you're doing there is you're just calculating what P of t is. So P of t equals Y of t minus 1 divided by M of t. So you're just rewriting P of t in your expression here. And that gives you your estimate for N of t. Does this make conceptual sense? Seems fairly straightforward, right? You have a population, you mark some, you put them back into the population. The ones you recapture are a little mini representative in the entire population, and that gives you an estimate of detection probability. Now, uncertainty is a fairly daunting looking equation, but as long as we keep track of what everything is, it's just adding and multiplying and dividing. We do have a power in there too. But y of t minus 1, the number captured on your first attempt plus 1. Y of t is the number captured on your second attempt plus 1 times y of t minus m of t times y of t minus 1 times m of t, and then m of t plus 1 squared times m of t plus 2. So all we have to do with this variance of n of t is keep track of these numbers, y of t minus 1, and m of t. And we can plug this in the equation, make sure we do our order of operations correct, and that gives us the variance of n of t. And then if we want a standard deviation of our variance estimate, we can just take the square root of that. And then to get our confidence intervals, you can use either 2 times the standard deviation, we have plus or minus, or 1.96 gives us 95% confidence intervals if we're using the normal distribution. You can use 1.96 or 2 in this class. Either one is fine. So similar things to what we've already done with parameter estimates. Now our parameter estimate is n of t, the total population size. We want to estimate some uncertainty associated with our population estimate, and we can use this equation to do that. These plus 1s and plus 2s are called finite population correction factors. So this relies on some survey statistical methods called design-based surveys, based on assumptions of how we collect the data. And when we do that, we have some nice finite population correction factors for that. We're not necessarily talking about those characteristics in this class, but that's where these plus 1, plus 2 information comes from. All we need to know is the equation for the variance of n of t, and that'll allow us to plug in our values for our data here and give us an estimate of variance. Then we need to know how to convert that to standard deviation and make uncertainty credible intervals around our parameter estimate n. Okay, we kind of touched on some of the assumptions here of this estimator. So we have to make this, for this to be valid, some assumptions have to be met. Assumptions about the population. And if you can meet these assumptions, this is a very nice way to go because it's fairly simple to mark some, well, depending on what type of animals you're using, but you can, in a lot of cases, you can mark individuals, release them in the population, you meet the assumptions, you can get estimates of abundance, and you're good. So here are those assumptions. The first one is the population is closed so that n doesn't change between your time intervals. Now in the Henzo sparrow example, we've talked about that they actually did 2 surveys for the Henzo sparrows. An original survey in June, then a second survey in July. What happened when they designed that survey that they didn't realize was that there was a lot of agriculture going on around the refuge. And they would have some grass fields out there and they would hay the grass fields. And after they hayed the grass fields, they'd have a huge influx of birds come onto the refuge. So this violates this assumption that the population size was closed on the refuge because between time intervals, they had a number of immigrants into the population. So what that is going to do is when you release the population back into the small population back into the big population, if you have a large influx of new individuals, the probability of recapturing your marked individual gets smaller because there's just more individuals in your population. So you're going to estimate your detection probability to be way smaller than what it is. And then your abundance estimate is going to be affected by that as well. So if you're not going to have unbiased estimators of abundance and detection probability if you violate this assumption. So when we talk about the BIDE model, population size at n of t equals the population size of n at t minus 1 plus births minus deaths plus emigration minus immigration plus immigration minus emigration. All of those four parameters, births, deaths, immigrants, have to be 0 for this method to apply. So you're going to want to make your marks, your releases, and your recaptures fairly close together. You're going to want to design your survey so that you meet these assumptions. So if you know what population you're trying to estimate the abundance of, and you know something about how that population moves around in time, you're going to want to develop your survey so that it meets these assumptions. So that's how you tailor your survey methods to meet your data analysis techniques. For example, with the Henslow sparrows, if they had marked birds and released them into the population, if they went back the next day instead of the next month, that may have given them valid estimates of abundance. There is another assumption here. Individuals do not lose marks between the two sampling periods. I think Brianna touched on this earlier in the class, where if you mark an individual, then release it, that individual has to retain that mark. If you lose it, it's going to seem like your detection probability is biased low, because you're going to have your animal captured a second time, but without that distinguishing mark, it's going to seem like an uncaptured animal. And when you do that, your detection probability is going to decrease, your estimate of your detection probability. So with lots of waterfowl, they use aluminum bands and plastic neck bands sometimes. And if those fall off, you're going to get biased estimates of abundance. So what they've done is look at individuals by marking, putting 2 marks on the individual. And then it's kind of a mini mark recapture study within a study. So if you put on 2 leg bracelets of waterfowl, 1 on each leg, and you recapture that individual, and you find an individual that's lost 1 but not the other, it's kind of like a mini mark recapture study where the marks are each individual leg. And then you can get estimates of how many marks are lost. So this assumption says individuals do not lose marks between the 2 sampling periods. If you have additional information that can tell you about how many are lost, then you can supplement these models, just make them more complex to estimate how many marks are actually lost. But that requires much more detailed information and further investigation. Another assumption is that all individuals have the same probability of being captured. So why might this assumption be violated? Let's pause to think about this. Especially with wildlife.
Maybe if it's harder to find a certain gender, like if the females like hide more or something like that, and the males are a lot easier to find.
Right, yeah, that's the case with waterfowl. So you might have some sex bias in there where males are, well, they're more conspicuous in waterfowl, they have brighter colors. And the behavioral response, like females sitting on nests, makes them more difficult to see. Okay, so yeah, how could we address that?
Only do a mark for 1 gender, so you're only looking for females and only looking for males.
Yeah, exactly. You could subdivide your population into 2 groups. 1 group that are males, 1 group that are females. So that's one way you could address that. Well, what about not necessarily groups of individuals, but just individual behaviors?
You mean kind of like how in the Amazon it's known that there's a habit for jaguars to be melanistic, and therefore you've got a subset of the population that you really can't find easily?
It sounds, you're going to have to give me a little more details. So melanistic, what is?
Melanistic, it means they're like pure black. What we call black
Oh,
panthers are
okay.
technically jaguars, and they're found in the Amazon. They have a higher tendency to melanism, to hide better because it's favorable. So
Okay,
it's a
so
subset of the population.
some individuals have different characteristics that make them camouflaged, more camouflaged. Right. Yeah. What about behavioral responses to traps?
Trap shy and trap happy.
Exactly. So you put out some Sherman traps for rodents. In these Sherman traps, you bait them with peanut butter to try and get them to go and steal traps. Some individuals may like the reward of peanut butter. Some may hate the fact they have to sit in a trap all night. And once they get trapped, their previous experience is going to affect whether or not they go back in that Sherman trap. So some individuals have behaviors that make them more likely to be trapped. Some individuals have phenotypes that make them less likely to be trapped or more likely to be trapped, and so on. There's just a lot of individual variation in behavior and capture probability that can make these an issue. And now if the population's relatively homogeneous in these traits, and some have them, some don't, it gets washed out if you have a large enough sample size. However, in some cases it can be an issue, especially if you're using any type of bait to trap an individual, and if the animals have very poor experiences in the traps. Okay, marking animals does not affect catching them. So this applies to, suppose, oh, I wanted to show some pictures. Let me see if I have these. I think we'll have a little bit of time at the end of this lecture, and I want to show some mark recapture studies in the old days. This applies to, you put a mark on an individual, that may affect the individual's ability to be detected. So one place where this comes out is with banding waterfowl. So a collaborator of mine, Chris Nicolai, has this theory that all of our, not all of our, but a lot of our estimates based on waterfowl banding data are biased because hunters target birds that have leg bands, neck bands. And when they target those birds, they then report those birds. They get the band, and if they want to contribute to science, they can take the numbers on that band and send it into the bird banding lab, and then we have data on that individual. So if an animal is banded and that affects its survival probability, we're not talking about survival probability yet, but the concept is still exactly the same. Then the fact that we marked it is affecting whether or not it's captured. That can bias our estimates. So if you have a big bright collar or a big ear tag on a deer, and that deer is now easier to see, so you see that one instead of another one, that can bias your estimates. Probability of capturing animals does not change in time. So for example, bears in the first sampling event are not in hibernation, and the second sampling event they go in hibernation. That would be a poor study design. You want to try and design your study to meet all of these assumptions. Okay, now this, despite its simplicity, is used for a lot of modern studies on abundance estimates. So I have a few examples here. Mark recapture accurately estimates census for Tatara, a burrowing reptile, Tawatara, burrowing reptile. From some people in Alaska, San Diego, New Zealand. Harvest survival and abundance of mid-continent lesser snow geese relative to population reduction efforts. So this is from Ray Alasauskas, who just received TWS award this year. I forget which one. But a lot of waterfowl work is based on Lincoln Peterson estimates. And then you see Lincoln estimates of let's see, waterfall, after Hatchier and Hatchier waterfall groups. So a point here is a lot of current studies are based on Lincoln-Peterson methods. They are the simplest form of recapture estimates. And you can, as an exercise, if you want to test that these methods actually work, we used to do that pre-COVID, we would do this in class. Take a brown paper bag, fill it with some type of bean or whatever you want, marbles, anything. Pull out a sample, mark them with a Sharpie, put them back, shake it up, pull out another sample, get your 2 counts, and then estimate how many beans are in the bag. And then you know how many are truly in the bag because you have a closed sample of your brown paper bag, and estimate how closely your estimate gets to the true population, and see if the confidence intervals overlap what the true value was. So you can prove that these methods work well. If you redid that experiment 100 times, about 95% of the time, your confidence intervals should cover the true population size. So it's that simple. All right, now you can take the methods we just talked about, our Lincoln-Peterson methods, and we can actually do more than 2 capture events. And if we want to do that, we can incorporate all the information from all of our capture events into our estimates using this equation here. So this slide here is for your reference. If you have a study that you want to design that has more than 1 capture events, you can use this to estimate it. Okay. So let me see if I don't have these images now on wildlife mark recapture in the old days. I'll share them in lab. Let me just do a quick search here. Okay. So these are photos taken from Dave Meach. Dave Meach is probably the world's preeminent expert on wolves. He's nearing retirement now, but he's had, I think his nickname is the Alpha Wolf. And he's been, for a long time, one of the leading wolf scholars in the world. He has somewhat, he has fame in popular culture too. I think he's been on the Carson show, and is well known. He started the International Wolf Wolf Foundation that has a place up in Ely, Minnesota, and anyway, famous wildlife biologist from the old days. He grew up just interested in trapping and hunting and fishing. Still traps mink every week, every fall for a week. I think he goes up there, but is definitely nearing retirement, if not retired already. So he has these photos that he took when he was in graduate school about wolf research and how they used to do mark recapture studies. let's see. All right, so this is from Dave Meach, scientist and wolf researcher. You could find this website online. And here are some photos. They would go out, capture some bears. And here is a leg hold trap. At a bear den here. Steel foot trap buried on a box formed by guide sticks. So the bear steps in there. They capture them. So this is way before days of IACUC, international use and care of animals, and guidelines and everything. So it was kind of like the Wild West when they were doing these studies. And this predates radio telemetry, any type of modern technology for studying wildlife. They essentially knew very little about wildlife in these days. Okay, so you have bears that they capture. Once captured, they put a neck snare around them. They tie him down by roping up all of his legs, and then they sedate him using, I don't know what they would use then. I'm sure it wouldn't be approved now. They capture him, sedate him, mark him with ear tags, and take some measurements of like snout length and tooth length. They weigh them. They remove a testicle if it's a male for histological studies. Yeah, histological studies. They take pictures of people riding the bear. It looks like they're having a tea party over here on the right-hand side with the bear. Dave Meach is pouring the tea right here. And here's the interesting part, right? So they had no technology, no radio telemetry or anything. So to get one relocation of this bear, they take a can of paint and they paint the bear orange just to see how far it actually moved. And this provided, as simple as it was, and as little information as it was, provided a ton of new information to them at the time. They had no idea how far bears moved, traveled, or whatever. But now they can actually get a recite of this bear for however far it moved, and they can see how far it went. So very crude technology and methods in the early days. And we can see that this actually violates our assumption of recapture probability for Lincoln-Peterson methods because this bear is definitely easier to respot than other bears. But that one data point provided a ton of information for them back then. And I don't remember, I think this was in the 50s that they did this. So since these studies, Meach went on to Yellowstone and studied a lot of the wolves. He went on up to study the Isle Royale population of wolves and population fluctuations with wolves and moose. And then has studied a number of other populations in Alaska. All right, any questions on this? In lab today, we'll talk about mark recapture methods, the Otis 1978 methods on the 4 or 5 different models that they wrote on mark recapture back then, and talk about lab 6. And I have office hours now, so if anyone's having challenges loading in data for the exam or wants to troubleshoot data loading questions, I'll talk about that to the extent I can. Okay, thanks.